All right, hello everybody. Welcome back to the third part of the multicollinearity lecture. We're going to talk about how to fix multicollinearity, right? The idea being that we've come up with ways to measure it using the Eigen decomposition and the variance inflation factor. Before I do, though, I want to just tie up a loose string that I left from the last lecture, which is we were talking about the Eigen decomposition of the covariance matrix of the bike data from the first DAP. Okay, so let me just go ahead and demonstrate how to do that in R. Talked about how to compute the Eigen decomposition in R. Flipping around too quickly. So let's just look at this really quick, and I'll talk through it, and then we'll get started on the next part, which is how to fix multicollinearity. So what I'm going to do here is I'm going to read in the bike data from DAP1. Okay. Well, remember what these variables are. So here are my column names, and then what I'm going to do is I'm going to code a bunch of the variables which are categories. I'm going to make sure that R knows that they're factors, and if I do that, then that will make it so that when I build linear models with them, it automatically makes them binary predictors and not treating them as numbers. So this is just a simple for loop, looping through the factor variables, making them factors. Okay. And then I'm going to use this model.matrix, which is a way to build the design matrix from a data frame. Okay. So here's my design matrix X, and I'm going to compute the Eigen decomposition of the variance covariance matrix of these predictors. Okay. So just to be clear here, let me see. So So this predictors is this matrix here, and well, let me just grab the first column, and I'll show you what this looks like. Okay, so this is grabbing the first column, which is unsurprisingly all ones. This is the design matrix course. This is the column of design matrix corresponding to our y-intercept. If I grab the second one, this corresponds to it looks like the season variable, right? So this is zeros and ones depending on the season. Actually, this can't be the season because I only have. Oh, it would be maybe it's the fall season or something like that. But they're corresponding to a binary variable. Okay, so then I'm gonna construct the Eigen decomposition of the variance of these predictors which I've defined. Okay, and so if I get the eigs, if I run eigs here, I'll get the eigenvectors and eigenvalues. Okay, so this is just a lot of information to parse because there's many predictors here. There's 30, but what I have here is the 28th, 29th, and 30th eigenvector, which I was discussing in the slides in part 2 of this lecture. And we see that if you break it down, so a lot of these are zeros, right? This is 10 to the negative 16, or sorry, this is 1 times 10 to the negative 16. So this is 0, 0, 0. And then these ones are not 0, okay? So on this run, it looks like what has happened is that it's actually switched the order of these two 0 eigenvalues. Of course, they're still in the order that we would expect. This is the one corresponding to the y-intercept, the all ones column, and this one is the one corresponding to the days of the week plus working day plus holiday. And then this one here is this one here is corresponding to temp and atemp with predictors 27, and 28. Okay, so this is just how to do this in R. Okay, so let's turn back to the slides, and we will continue talking about multicollinearity, and in particular, we're going to discuss how to fix it. Okay, so the first option is that we can drop guilty predictors from our models. Okay, so what's a guilty predictor? Well, predictors which appear in the principal components which are or near degenerate, right? So in the example from the bike data that we were just looking at, this days of the week plus holiday plus working day, we can drop one of them or all of them, and this will fix our degeneracy. Okay? If you have a few non-zero predictors in a degenerate principal component, this is a reasonable approach, but if there are many predictors, choosing which one to remove can be difficult. So again, thinking about the bike data example, we have days of the week plus working day plus holiday. Which one of those should we remove? If we remove one of them, we can correct our multicollinearity. But should we remove Monday, Wednesday, holiday? It's unclear, right? So if you have, for example, two predictors and you can just pick one and drop one or drop the other one and test really quick, this is an easy way. You can correct the multicollinearity, but actually correcting it in a way that still allows you to build the best model can be difficult. Okay, so that is one option, and it's a pretty intuitive option, right? You found via your eigen decomposition an eigenvector which gives you the linear combinations of predictors, which is at or near zero. You can try and get rid of one of those predictors in a way to correct the multicollinearity. Another way that we can actually correct this is to actually use these principal components, i.e. these eigenvectors. We can define new predictors using our principal components. So let me explain what's going on here. But what we'll do is we'll actually define new predictors as linear combinations of predictors from our old predictors. And these linear combinations are going to come from our eigenvectors. Okay? So this is basically what I just said. New predictors from old predictors by taking linear combinations of the original predictors, and the linear combinations are given by the eigenvectors of our covariance matrix. Okay, and what we can do is basically just reduce the number of predictors by only taking a certain number of eigenvectors. So we're going to define predictor 1, the new predictor 1 corresponding to the linear combination of old predictors by the first eigenvector, the same for the second, the same for the third, and we can go on until we reach some eigenvector threshold for which the eigenvalues get small, and then just take those just cut off there and reduce the number of predictors we have. Okay, so this is, we can not include degenerate linear combinations or near degenerate linear combinations of predictors. So this method is called principal component regression. The idea is that we're using the principal components, the eigenvectors of the covariance matrix, to do regression. We're using those other new predictors. Okay, it's also called PCR, principal component regression. Okay. In general, if you build new predictors from the principal components of the original predictors, this is called principal component analysis, or PCA. So PCA is useful beyond just linear regression. In our context in this class, we will always be doing principal component regression. But if you have another problem and you want to look at, you're not just doing linear regression, you want to look at principal components, then you would call it principal component analysis. And as I say here, you can use it beyond linear regression. So this is one of the reasons we're actually introducing the eigen decomposition here, and these principal components, and this idea that we can detect low variance and high variance linear combination of predictors, is because it's actually useful in linear regression, but also outside of linear regression. Okay, so let's look at the recurring example that we had, this correlated predictor model, right? So here's predictor 1, here's predictor 2. They're obviously highly correlated. We've looked at their eigenvalues and eigenvectors previously in the second part of this lecture. So how should we choose K, i.e., how many principal components should we use as predictors, and which ones should we discard? Okay, the idea is we want to capture the high variance terms and discard low variance terms. Well, I'd remove this one, right? And I'd just take K equals 1, and I'd reduce this to a single predictor, which is this predictor formed as a linear combination of predictors here. Okay, it's in this direction. I guess this one is technically in this direction, but same idea. Because this has a high eigenvalue, this direction has a low eigenvalue, I would say trash it, and then I would get rid of the degeneracy, just reducing from 2 predictors to 1 predictor, where my 1 predictor is now in the high variance direction. Okay, so the idea is we capture most of the variance in the predictors this way, and we're discarding the rest. Okay, so how this actually happens, okay, so we build a new predictor Z, which is the linear combination of predictors according to that first eigenvector, right? So here's the new predictor. And then we would regress y, our response variable, onto this new predictor z, which we formed taking the linear combination of old predictors according to that eigenvector that we want to keep. Okay? In general, you can build new observations from old observations using some clever linear algebra. So this one we can see by hand. It's kind of easy to do. You just grab those components, grab those, they're sometimes called loadings, grab the loadings of this principal component and form your linear combination of your predictors accordingly. So this is your new predictor. But in general, to compute new predictors from old predictors, you can actually construct your observations using the following. Okay, so here's z. This is your new predictors. Okay, and x is your old predictors, and v is your eigenvectors. Remember, this V matrix has your eigenvectors as columns. Okay. And so this will give you the new z's. You can then select, right? So you can select the v's. If you only want a certain number of eigenvectors, you can just only keep a certain number of columns. Okay, so this is just projecting x onto these various eigenvectors. So you can just sort of select a certain number of the columns that you want to keep, do this projection, you'll come up with z, which will have however many columns you kept in V. Okay. Another way to do this is actually using the PRComp function. So this is not in a package, this is just in base R. It will construct your principal components directly from your data. Okay, so that it will come up with it can do it would do this projection for you. Okay. I don't think that it's necessarily easier than just doing this matrix multiplication once you understand what's going on, but it's built in if you choose. Okay. So alternatively, doing it manually once or twice I think helps us cement what's going on. Once you've done it manually a few times, I encourage you to use pre-built tools. So for principal component regression, the PLS package contains the PCR function, PCR being principal component regression, which will allow you to build principal component regression models directly from the old predictors, the original predictors. Okay. The caret package is useful because it provides a unified interface for principal component regression and many other important methods, which we're actually going to discuss in this class. So what caret does, it's kind of nice, there's a bunch of different tools to do different things in R, and caret says, oh, maybe I can unify them and provide a common syntax so that you can instead build models in caret, and caret will feed the information to the PCR function in a unified format. And I encourage you to dig into caret. Sometimes when you have to do some unique things, caret won't support it, and you can go into the PCR function directly. But the reason I encourage you to learn caret is that we'll investigate some other methods as we move forward, which will also have nice caret interfaces. And so if you learn caret, it'll be easier for you to spin up those models. Okay. Caret will also do something really nice for you, which is that it will select these number of principal components. I have it here automatically. We'll talk about that in a little more detail when I run the R example, but it'll do this for you, okay, which is nice. So this automatically, as I say, we're going to discuss it a little more in the R code, but this is actually what it does is it's called cross-validation. So cross-validation is how it will select the best number of components K to keep. And so, we'll talk about that. So cross-validation is the following idea. So we're going to choose a tuning parameter. So a tuning parameter is just something that we have to sort of pick to build our model. So that is how many principal components do you want to keep. Okay. So to do so using cross-validation, you do the following. So you partition the data into m different sets, And they should be about here. They should be of equal size, approximately. Okay, you don't want to have one extremely large and one extremely small. So we're going to partition the data into m different sets. Okay, we're going to for each of the partitions. Okay, so that is or for each element of the partition, that is for each of the subsets, we're going to do the following. That is, we're going to use the current subset as a test set and use everything else as a training set. Okay, we're going to compute the testing error, so usually this is root mean squared error, for a range of possible tuning parameters, and then we repeat this process over all the different possible testing sets we can have, and we select the tuning parameter which gives us the lowest score on average for all the testing sets considered. So I think actually this is kind of clear as a picture. So you can imagine this is our data. Okay. So it says partition the data into m sets, so I'm just going to do 3. Okay. And so what we do is we say, okay, here's my observation. Here's 3 groups of observations. So I'm going to choose this one. What I do is I'm just going to number them a second. I'm going to choose this, start with this one. This is going to be my testing set. And then these 2 are going to be my training set. I'm going to build a model and build models, I should say, for a range of tuning parameters. So I could say like tuning parameters, I'm going to keep k goes from 10 to 11. From 10 to 11, I'm going to compute the models with k equals 10, k equals 11, so on and so forth, and compute the testing error with this as my testing set and 2 and 3 as my training set. And then I'm going to repeat. I'm going to go to 2. 2 is going to be my testing set. These are going to be my training set. I'm going to build a bunch of models for a range of tuning parameters and continue on. This is going to be my testing set. These are going to be my training sets. Or these 2 combined is going to be my training set. And I'm going to compute the testing error for a range of possible tuning parameters. Okay? And then I select the tuning parameter which has the best testing error. Again, we're going to be using RMSE primarily overall. So so I'm going to have considered a range of tuning parameters for different testing sets. They're all going to have an average performance over all of these different splits here, and that's going to be my best. That's what I'm going to choose according to cross-validation. So this is called cross-validation. It's called m-fold cross-validation because we're partitioning to m different sets. Usually we call m-fold cross-validation is called k-fold cross-validation. This is just a language thing, but we're using k to discuss the number of principal components, so I'm just going to call it something else, m-fold. Using m is not really typical, but it's just a dummy variable, so I've just used m. Okay, so let's switch over to R for a little bit. So we're going to do 2 examples in R. We're going to do PCR on principal component regression on the correlated predictor model that was simulated. So remember, this is the x1 and x2 are correlated. We're going to construct new predictors using the Eigen decomposition. We're going to construct new predictors using PR comp. Okay, we can do both of those things. Then we're going to look at a second example, which is on the body fat data set from the interactions lecture. So if you remember that, we had a number of individuals. I think it was 250 individuals where we had measurements of their bodies. It was like their bicep circumference, their hip circumference, their age, their weight, all these different things. And we're going to try and predict percent body fat using PCR. Okay, we're going to build new predictors using Eigen, using PR comp, and we'll also automate PCR using this caret package that I was talking about earlier. Okay, so here we are. So here is the correlated model that we simulated. Okay, so I'm just continuing on in the R code that I've been working in before. So I'm building a design matrix. Okay, here I've omitted the column of ones. Okay, and what that does is, as we discussed, that column of ones is always going to have 0 variance, so I can omit it, or if I keep it, I know what I'll get out of it. So I'm going to construct the Eigen decomposition. Here's the eigenvalues, here's the eigenvectors. We've seen both of these numbers before. This was the linear combination of predictors, this first column, which had high variance. The second column had low variance. Okay, and these eigenvalues, again, this one being small, this one's my degenerate linear combination, or nearly degenerate linear combination. Okay. And so what I'm going to do is I'm going to select just the first column from these eigenvectors. These are my selected principal components. Okay, so this is the first column. And then I'm going to do that x multiplied time, or x matrix multiplied, so my design matrix projected onto the eigen the eigenvectors which I've selected. So I've selected the first eigenvector, constructing my new predictor. My new predictor is now given in this z variable. Okay, it's a column vector. The reason is that there's only a single predictor because I've only selected one linear combination of predictors to keep. Okay, my PCR model, I'm going to regress y onto z. Remember this y3, if you don't remember the naming convention, this is because this is my correlated predictor model. And my PCR model, what happens is I have an intercept, I have a z, so I'm building a new model using just the single z predictor. And this allows me to overcome the multicollinearity concerns because I have thrown away that linear combination of predictors, which was problematic. Okay, so we can also compute the principal components using the PR comp function. Here's how we do it. Here I have the principal component 1, the principal component 2, and then here's my projection onto those principal components. So this first vector gives me that z that I had defined. The second one corresponds to a variable. This is the linear combination of predictors corresponding to the second eigenvector. This is the one I threw away. So I can throw it away here, or I can throw it away by just not projecting onto that eigenvector in this matrix multiplication. But then PR comp, it will project both, and so yeah, so that's what we see here. So this second linear model, I'm doing exactly the same thing. Here I'm just grabbing the principal component corresponding to, or I'm grabbing this is my z, this is the projection onto the first eigenvector. Okay. And here we have this PR, this is projection onto the first eigenvector using that z. These numbers, unsurprisingly, they match. Okay. So that is, I've used PR comp, or I've done it by manually doing this projection of the z, and we see that we have the same model. In general, I will say this, it's generally recommended, and I recommend, that you scale the predictors. And what I mean by that is subtracting off by its sample mean, dividing by its sample standard deviation. When you do this, you're going to reduce the effect of extremely high variance predictors. So you're making all the predictors have sample variance 1, and that way you can consider their interactions among each other instead of just things being blown up by predictors which have high variance. So the PR comp function allows you to easily scale your predictors when you're coming up with your principal components. And so with the scale equals true, center equals true. So this makes your sample mean 0 of each column, sample mean of each predictor 0, sample variance of each predictor 1, before you do the eigen decomposition. And so this is a model where we've accounted for that. Okay. So let's do the next part, which is the body fat data. So here's reading in the body fat data. Remember, we had all of these different measurements. Okay. I'm going to build this matrix. So I'm going to select everything except the density variable and the percent body fat. The idea is that I want to predict percent body fat. Density was this expensive measurement which wasn't realistic to collect in practice. And then by doing +0 here, I'm going to omit the ones column from my design matrix and do that for the same reason that I did above. I know what I'm going to get out of it, and that is a no variance in that column. So do my eigen decomposition. Here's my eigenvalues. Here's my eigenvectors. Okay. So let's just look at this. So here's my eigenvalues. Okay. So again, I'm looking for small eigenvalues. This one here is very small, 10 to the negative 14. These ones here are 0.02, 0.2 and 0.9. And so this one here is basically numerically 0, right? This is 10 to the negative 14. So this is something perfectly degenerate. So let's go to the 14th eigenvector and look what's going on there in terms of our linear combinations of predictors. So these ones are all the other ones are very small, but these two, predictors 6 and 7, play a large role in the in this eigenvector, right? We see just by the size of their coefficients. And so, what are predictors 6 and 7? Well, let's grab them. They are abdomen and waist, okay? And so what we see here is that the eigenvector has allowed us to detect that abdomen and waist are highly correlated. Including both of them in a model would give us degeneracy. And so we'd want to include one or the other, right? Makes sense that abdomen and waist would be highly correlated, given I'm not sure how I would distinguish in a measurement between an abdomen and a waist. I think that for colloquial English, they would describe the same thing, but maybe if you're a medical professional, they're slightly different. Okay, so as I talked about, we could exclude one of these to get around our collinearity issues. We could also do something like principal component regression. So here I'm going to project X, the design matrix, onto the first 13 eigenvectors. I'm going to omit the 14th because that was the degenerate one, right? So if I look at the VIFs of this model, where I'm using these projected predictors, the VIFs are 1. Okay, so this is the best case scenario. But this is just an artifact of doing principal component regression. When you do principal component regression, these eigenvectors, you can convince yourself of this if you'd like, but because these eigenvectors are orthogonal, these new z's are going to be uncorrelated. Okay, and because they're uncorrelated, your VIFs end up being as good as you can be. Okay, you don't have any correlation among your predictors. And the original model, if we're not doing principal component regression, the original model is not able to assign a coefficient for each one of your models. And R says, R tries to be clever, and it throws out waste automatically. Okay, so R has said, oh, you tried to build a model, I couldn't invert X transpose X, so I'm going to throw out one and try and invert it. And so it threw out waste, because you could not have a model with abdomen and waist because of that degeneracy. Okay, so I'm going to gloss over this, but just say that you can use PR comp to construct these new predictors, and the benefit of that is that you can scale your predictors, center and scale your predictors easily that way. Okay, but the idea is exactly the same. Okay, so let's do I mentioned that we have a PCR function from the PLS package. Okay, so if I load up the PLS package, I have this. I can use this PCR function to build a model. So I'm going to predict percent body fat from everything except density, and the number of components that I'm going to use, the number of principal components that I'm going to use to build my new predictors is going to be number of columns of X minus 1. That is 13, throwing away the one we know which is bad. Okay, so here I'll just point out, right? Unlike the LM function, I have to give PCR this ncomp, which will tell me how many components to keep. Okay, so the PC model is it has some different syntax. Okay, so it's not just going to print print my coefficients as with the LM. It does things a little bit differently. But we can use things like coef, predict, resids, all these things in this PCR model. It will work with all those. So I can do something like coef PC model. And here they are. Okay, so it says there's 13 components, and here are the coefficients associated with each of the old predictors. To get the coefficients for each of the old predictors, the original predictors, what it does, because you remember each of the coefficients, each of the predictors are these z's, right? What it does is that each z can be written as a linear combination of the old predictors, and each z has a coefficient, and so by expanding out the z's into their linear combinations of old predictors, you can actually come up with coefficients for each of these predictors, and that's how it gets that. Okay, same thing in caret. So caret is a little harder the first time you use it, but again, the idea being that it'll automate some things, and we'll be able to use it with more models. So I'll load up the caret package. And then, so what I'm going to do here is I'm going to build a PCR model in caret, okay? And I'm going to use the train function to train a model predicting % body fat from everything except density using the PCR method. Okay, so this is the caret syntax for building a PCR model. And so, let me just print out what we have here. So what happened is actually it used, so this is trying to choose the number of components for us. We didn't give it quite enough information, but we have RMSE going down. So this says I tried to build our model using 1 to 3 principal components to build our z's, our new predictors, and it did so not using cross-validation, but using something called bootstrapping. I want to make it use cross-validation, so I'm going to specify the following. So here's I'm going to specify two things. I'm going to specify that I wanted to use this train control. I wanted to use cross-validation, 10-fold cross-validation. Okay, so we've talked about this repeated train test splits, so there's going to be 10 different testing splits to consider. And then the number of components that I want to consider, I wanted to go from one component to all the components possible. Okay, so let me just run this. It's going to take, it took a little longer, but it was still quite fast. And when I look at this now, this caret model tells me, so this is the average performance across all the testing sets in the cross-validation when we're doing cross-validation. So this is the average RMSE over those different testing sets, and here we see this average RMSE exists for each of these number of components. So we can see that the RMSE goes down, 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 down. It goes down, it goes up, then it continues to go down. Then we see 13 here. This is good. This is the lowest. With 14, when we include all the predictors, actually the RMSE goes up. Okay. So then caret will tell you something nice. It says, oh, we've done cross-validation. We've used RMSE to select your best model, and if we do that, the final model has 13 components. So we selected that by hand by throwing away the one of the principal components, which gives us that degenerate linear combination with waist and abdomen, and actually automating that process via cross-validation in caret gives us the same result. Okay, the idea being that it's easier. Well, when we can't examine it by eye, caret will do this for us. Okay. In general, caret's output is not actually a model. So to select the best model, use this $ final model. So this selects the best model. We can use predict, resid, coef, exact as we would for a typical linear model. But this is going to be, technically, it's going to be a PCR model under the hood. So this is using the PLS package. So it's a little different than LM. Uh, but yeah, so that's how we will get the final model from a running caret. Okay, so this train function, I mentioned this before, it's useful. It automates cross-validation for us, and we're going to see it in the future. So dig into it a little bit. So and then I mentioned this, but we can extract coefficients from our models using the coef function as before. We can actually select the coefficients according to each component if we'd like, or a range of components if we like. By default, this will return all the coefficients across all of the principal components. Okay, so that is principal component regression and how to do it in R. So takeaways from principal component regression. The pros of it is that we can generate new predictors which are uncorrelated from the perspective of multicollinearity. This is the best case scenario for us. So if we want new uncorrelated predictors from original predictors, this is how we do it. It can be a little bit difficult to interpret because, right, we're like constructing these new predictors and then building a model based on these new predictors. We can still pull these coefficients back into old predictor space, but in general, it's kind of, right, there's a lot going on and a lot of moving pieces. It can be harder to explain. And so that's just a trade-off we get for being able to correct multicollinearity. As a con, it requires some linear algebra skills, right, to understand what's going on under the hood. I would phrase this as not a con, but a pro. We have some linear algebra skills. You've taken linear algebra classes before. So my pro is that we can actually apply the linear algebra that we already know and shake the rust off of them and those skills and put them to good use. Okay, so that's principal component regression. There is another way to solve multicollinearity. It's called ridge regression. Okay, so ridge regression is this interesting technique where we basically we swap bias for variance. The idea being that we will introduce an estimator of our betas, which has bias in it. Okay, so we've talked about before that beta hat, the least squares estimator, is unbiased, and that means that in expectation, beta hat is equal to beta. But when we swap bias for variance, the idea is that we would be willing to give up a little bit of bias in exchange for lowering our variance, and we hope that we could reduce our MSE, our mean squared error, overall. Because remember, in way back in lecture 1, we talked about how mean squared error can be decomposed into squared bias plus a variance term plus some irreducible term in terms of the noise of epsilon, the variance of epsilon. And so in this equation, if this is 0 and this is large, this variance is large, maybe I would perform a trade-off where I would say, okay, if I get a little bit of variance for or a little bit of bias, for a large reduction in variance, I might be willing to make that trade for lower MSE overall, right? So yeah, that's the idea of ridge regression, is that we swap bias for variance. We would reduce the variance, introduce a little bit of bias, and in that way get around not so much multicollinearity in terms of the degeneracy of the predictors, but multicollinearity in terms of its symptom being high variance of our beta hat. That high variance is bad for us, and so we can just correct the variance directly without having to throw away predictors or change our predictors. So ridge regression looks exactly the same as in multiple linear regressions. We have our design matrix, our y vector, our beta hats. Okay, this is built all as before. But instead of minimizing the mean squared error, we minimize this expression. Okay, so here we have, again, b is a dummy variable. This is the notation we've used before. So we're going to minimize over all b. Okay, these are our coefficient vectors. And again, it's p plus 1, p predictors, 1 y-intercept term. So this is the mean squared error, right? But I add a penalty to it, okay? This penalty here, I'll explain what this is, but this lambda is some coefficient, and here is the sample size, the number of observations we have, and b is our coefficient vector, okay? So this norm of b here is the squared length of b, okay? So this can also be written B transpose B. I can put an identity matrix in there if I want. This will be convenient for algebra later on. But what this is the inner product of B with itself, okay, i.e. the sum of the square entries of B. Okay, so what we're doing is we're adding this penalty for this coefficient lambda, for some scalar lambda. We're adding a penalty on the coefficients of B and minimizing this instead. Okay. Penalty parameter lambda. All right. So, I'll just say this in terms of notation. So some authors write lambda over n as just a lambda. Okay, so you can just say, oh, lambda over n is some penalty, right? You can sort of incorporate the n into the penalty term, or you cannot. Authors will write it both ways. So if you see it lambda without the over n, it means the same thing, okay? So the big idea here is that by having a penalty on the size of beta hat, we actually will, we reduce its volatility, right? So beta hat when we have multicollinearity issues, beta hat is bouncing all over the place. It has high variance, right? And so by adding this penalty, the idea is we can actually encourage it to stay fixed, to stay close to a certain point, to not bounce around so much. Okay, it introduces bias because we're sort of we're adding a penalty that encourages it to be something different than what the data suggests, but it doesn't reduce its variance. Okay, so we're going to compute the ridge estimator just using our matrix calculus, and we're going to analyze it using a truth plus error representation. We'll see that it's biased, which is sort of interesting because we've only been our least squares estimator is unbiased. So we're going to use the same old tricks that we've seen using the vector calculus to solve for beta hat, analyzing it using a truth plus error representation to examine it in some more detail. So we want to minimize the mean squared error, the empirical mean squared error, plus some penalty term. Again, as usual, what I'm going to do, well, actually, first I rewrote this in a way that makes it the algebra a little easier, which is that I rewrote it as the inner product of B with itself, and I put an identity matrix in there for a reason that will become clear in a little bit. Okay. So I'll expand out this this matrix multiplication. We've seen this before, but it actually turns out that these terms are scalars, therefore they are symmetric, right? A scalar, you can take a transpose. It's obviously the same quantity, and this is equal to this transpose. So I can just, these are symmetric, they're equal to each other. I can just collect them in this term. And so I'm going to take this term, which is just another representation of the original objective function, take a gradient with respect to this b term, and set it equal to 0. When I do that, the y obviously cancels. I'm left with the b transpose out front goes away. I'm left with this term here. And then here I have quadratic forms in b. If you remember what happens with that, you take a gradient, the front one cancels, and you get whatever's this term here plus this term transposed attached to your variable. Okay, so here I have x transpose plus x transpose x plus x transpose x transpose. That's because this matrix here is once and then transposed, and then the same thing for the beta, this second quadratic form. Okay. Solving for beta here, I get, I can move over, right, solve for beta, I get the following, okay? So what's happening is, instead of, right, this looks very similar to our least squares estimator. The only difference is that this lambda here, if lambda was 0, then I would get beta hat is x transpose x inverse x transpose y, which is our least squares estimator. For this lambda I here, for lambda not equal to 0, I'm adding something extra to this x transpose x, and the idea is that if this thing is near invertible, this thing will just shift it away from that a little bit. Okay. So that's the ridge estimator. And again, here's our comparison. And the idea being that lambda will introduce a little bit of bias. It will hopefully reduce our variance a lot, and the idea is that that trade-off might be worth it for us in terms of mean squared error. Unlike ordinary least squares, the ridge estimator will always exist. Okay, so no matter how much degeneracy we have in X, the ridge estimator exists, which is nice. We don't have to worry about this X transpose X not being invertible when we use ridge regression. And the intuition is actually, I think, it carries over from the scalar case. So in the scalar case, if you have something, so for example, you have A, which gets near 0, which goes to 0, and you want to invert it. So A goes to 0, you want to find 1 over A. As A goes to 0, this thing gets large, right? But if I add, this is just, again, just thinking about scalars, if I add some constant lambda here, this does not go to infinity. And it doesn't blow up the same way, right? Because as A goes to 0, I get 1 over lambda, instead of, right here, 1 over 0 going to infinity. Okay? So that's the idea. We're basically adding a constant bit to prevent this blowing up as X transpose X becomes non-invertible, or is near non-invertible. The truth plus error representation. So we've seen the truth plus error representation. So this is beta hat is X transpose X plus lambda I. So this is the ridge estimator. Okay, and I'm just going to plug in what I know for Y. Okay, this is an analysis we've seen. I'm just using a different estimator. Expand. But timeout. Here we see something that we did not see in the least squares setting, and that is that in the least squares setting, this term X transpose X inverse canceled with X transpose X, right? And so we were just left with beta hat is truth plus error. But we do not get beta hat equals truth plus error because we have beta hat equals something that's not the truth plus some error, right? So we actually, the analysis that we know, that we have seen before, fails because the fact that this is not the inverse of this matrix. The expectation of beta hat, right, from this expression, we can just apply expectation of beta hat to both sides. This term will become 0 if epsilon satisfies that first assumption from the first of the multiple linear regression assumptions, and we just get that epsilon of beta hat is equal to this. Okay, this is not equal to beta unless lambda is equal to 0. So here we see the bias. Okay, the variance of if we have a constant variance assumption, okay, that is the second assumption in the multiple linear regression assumptions, we can actually compute the variance of beta hat, but it's just gnarly. So it is, this is the variance expression. Again, we can just take the variance of this, using this no longer truth plus error representation. This is constant. This thing has to hang around, and in the least square setting, again, this canceled with this, and we are left with the variance of beta hat is sigma squared X transpose X inverse. So things are just more complicated from the analysis perspective, but again, this is a trade-off. We're trading this for reducing the variance. So again, we've reduced multicollinearity. We have more complexity in our analysis. We've introduced some bias. In how to actually use ridge regression, we're going to use caret. Again, I was suggesting that caret's going to be important for our upcoming topics. Here is an example. We can select lambda, this penalty, via cross-validation. Okay, and caret, under the hood, it relies on the glmnet package, but caret is nice because it provides, again, this consistent interface with which we can do things like PCR and ridge regression using the same syntax. Okay. Here, let me return back to this correlated predictors example. So this correlated predictors, remember I had this low noise model, this high noise model, and the correlated predictor model in blue. What happens if I actually run ridge regression here? So if I run ridge regression, I get this point, okay? So here, we've reduced the variance of these blue points, okay? So this is 100 iterations generating these samples, solving for these least squares estimator over here, and this is the ridge estimator over here in brown. And so here we have the points are much less spread out, right, than they were with the correlated example. So I've reduced the variance here, but you see that these are not centered around the truth anymore. So this is just demonstrating the fact that I have swapped bias for variance and in my estimate. Let's turn to our example. I'll remind you that I mentioned it's generally good form to standardize your predictors when using PCR for the idea that you don't want to have a single predictor with an outsized variance overly influencing your Eigen decomposition. It's the same in ridge regression, I think even more so, because your units of your objective function, let me just show you this really quick. But if the x's are not standardized, then when you construct this objective function, the units become very odd because you have mixed units between these quantities and between the MSE and the quantities here. So in general, it's good practice to standardize your x predictors. Okay, where are we here? Okay, so let's do this R example. So turning back to R, so I mentioned that caret for ridge regression uses GLMNet, the package under the hood. You'll have to install it if you haven't already. But you can do ridge regression in GLMNet using cv.glmnet. This is cross-validation.glmnet. Here I've fed it a formula. Okay, I've given it a number of folds in my cross-validation and standardize equals true. We can give lambda to this GLMNet, or we can select it automatically. Here, R has selected it automatically for us, as this is the best relative to the 10-fold cross-validation that we've done. Using caret, it's the same. We're just going to use the train function. We're going to use method equals glmnet. Okay, and we're going to do train control. This is similar to what we saw in the PCR example. Cross-validation 10-fold, and then for the penalty, we're going to take the penalty to be, I'm just going to do this from 0 to 1 of length 100. Okay? And then there's this extra alpha parameter, and this alpha parameter, we're going to come back to it later in the course, but for ridge regression, set alpha equal to 0. Okay? This will, if you set alpha equal to something besides 0, it's not going to do ridge regression for you. So by setting alpha equal to 0, we get ridge regression. I'm going to do this pre-process equals center scale so that I can scale my, I can standardize my predictors as I discussed in the slides. So here's a ridge regression model. I'll say, let's just pull this up here. This looks to be, oh, okay, so let me just pull up this example and we'll see what its output was. So we notice that I went from 0 to 1. So for my penalty parameter, look at all these different, my penalty parameter goes from 0 to 1 of length 100. So it's just a lot of different penalty parameters here. And sort of hard to look through. It's a big table, has my root mean squared error for each of these examples. And then it says RMSE was used to select the optimal model, and the optimal model was alpha equals 0. This makes sense because I said alpha is always 0, and lambda is 0.65. So 0.65 lambda gave me the minimal RMSE. Okay. Here, and so what I'm going to do next is I'm actually going to narrow in my possible lambdas. I'm going to narrow, if 0.65 was my best lambda, I'm going to narrow in that window from 0 to 1, to 0.4 to 0.7. Okay, so this is exactly the same. It's just that I am selecting a window around what was my best instead of going all the way from 0 to 1. So now we have lambda is 0.672 is best, and so that's the lambda that's being selected. And then I can get my best model using best model ridge. I'm going to select, I'm going to save this as best model ridge, extracting the final model from caret. Again, the idea being that we've seen this extracting the final model process before using PCR. We can do exactly the same thing to get the ridge model. To get the coefficients from the ridge model is actually quite a little bit awkward. This is because of GLMNet syntax. But what you have to do is actually provide a lambda value. And surprisingly, it's not called lambda, it's called S. So extract the coefficient, and you have to give it this S, which I'm going to say get the model which was the best, and using the lambda which was the best from my caret output. So here are my coefficients. You notice that we have abdomen and waist together in the same model, right? So this is as a result of using ridge regression, that we're overcoming the degeneracy using that penalty. Okay. So lastly, right, we've come up with two different methods to correct for multicollinearity. We have PCR, right, coming up with these new predictors based on old predictors and taking these linear combinations according to the Eigen decomposition. And we have ridge regression, where we add this penalty and swap bias for variance. So which actually performs best in the context of this body fat data set? So here we have, let's see, we say n equals 13. So this 4.33 is our test RMSE as assessed by this cross-validation when the number of components was 13. This is PCRs. And then 0.672, so 4.41 in the ridge regression model as compared to 4.33. So we see that PCR outperforms ridge regression by measure of root mean squared error, though they're a little bit on a similar scale. This won't always be the case that PCR will outperform RMSE, but we see that here it has. Comparing to the usual LM, okay, so here we see, you may have seen this before, here we see predicting from a rank deficient fit may be misleading. I hope this error makes sense. So what R is telling us is that, hey, your model is degenerate. You're trying to predict using an X for which X transpose X inverse is not invertible. And R tries to do something under the hood where it throws away a predictor and makes and fits just with an NA on some of the coefficients. But that's what this error means. And it's actually a warning because it's just doing it automatically, but letting you know. I'll also say that I used the caret method, the caret train function, to build a linear model. This is just using method equals LM, and in that way I can assess the test root mean squared error via the cross validation. Okay, so it's a sort of a common rubric for, even though I'm not tuning anything, it's a common rubric for assessing these models. Okay, so 4.33 was the PCR model. 4.32 here is for the LM models, and 4.41 I think for the ridge regression models. And so we see actually that the LM, there's a little bit, this is 4.33 to 4.32, right? These are basically equal. If you want to get particular about the second decimal place, you can. I'm not. But the advantage here is that we've removed the degeneracy, right? So each one of these models, so it's sort of misleading because when R is computing these models, again, it's automatically throwing away one of the predictors for us, okay? And it turns out that that's actually working okay. But this is not actually a model that uses all the predictors, right? Because of the degeneracy problems. So when we use PCR, we saw that we have, very similar RMSE, but we can get rid of that degeneracy and overcome degeneracy that way. If you're following along in the code, if you download it yourself from the course site, what happens after here is I made my graphics for my slides in this code, so you can go through that if you have interest. So a quick review. We've been a lot of places with multicollinearity. Let me just talk about what we've done and summarize before we conclude this long lecture. So we've talked about multicollinearity. It's a problem because the variance of our least squares estimator gets large. And that's in one case if we have near degeneracy, or the least squares estimator just doesn't exist because X transpose X inverse doesn't exist. Okay. We've talked about the VIF, the variance inflation factor. We can compute it in R using the CAR package. It gives us this VIF function. The pros of VIFs is that it's simple to construct, but the problem is that it does not actually help us correct the problem. It just measures when multicollinearity is a problem, right? So the Eigen decomposition, we can find which linear combinations of predictors are or near degenerate. Okay, that's helpful because we can actually find the guilty, I call them guilty, the nearly degenerate linear combinations of predictors. We can find them using the eigenvectors corresponding to the eigenvalues, which are 0 or near 0, right? In principal component regression, we use our principal components to build new predictors. The idea being that we throw away those linear combinations of predictors, or we don't use to define new predictors those eigenvectors which have low variance. Okay. It is a little tough to interpret, but what's nice about it is that actually we're diagnosing our problem with our multicollinear problem with the Eigen decomposition, and we're correcting it with the same tool, right? So that's kind of nice because if you understand Eigen decomposition well, you can diagnose and fix your problem easily. Okay. Lastly, we introduced ridge regression, and ridge regression, the idea is we add a penalty to our usual mean squared error, and we increase our bias, but we decrease our variance. Okay. The pro of this is that it's interpretable. So we have we still have all of our predictors in the model. The least squares estimator, or the ridge estimator, will always exist, whereas the least squares estimator will not. Sometimes, if X transpose X is not invertible, we have the con of, well, we're actually adding bias, right? So we have a trade-off there, and also choosing lambda. We have caret, which can automate this using cross-validation, but there is just a decision there to be made. Okay, so that is multicollinearity. It's a lot. Flip through the slides. I know there's a lot going on, but that wraps up our discussion, and I will see everybody next time.